Hello all. In this video, I'm going to walk you through a Google Colab notebook I prepared where I discuss various machine learning models you can use with a basic machine learning classification problem, okay? And in fact, we will talk about the XGBoost algorithm and as well as the RandomForest, the Logistic Regression, and the MLP classifier. And the MLP is a neural network, okay, that scikit-learn offers, okay. And we will also build the basic PyTorch implementation, all right, and also demonstrate how to build the basic Dash web application to deploy the models if you wish to do so. Everything will be run inside the Google Colab environment, but the same ideas can be used to run interactively in a local environment, for example, okay, on your terminal plus VS Code, for example, okay. All right, I think this is the first video. No, this is not the first video. This is the second video in which I talk about machine learning, because the first video was a video in which I introduced pins, as they are called. And pins, no, I didn't introduce them. I mean, I'm not the creator of the idea. I mean, I introduced them in terms of the channel that I'm running here, okay? So pins means physics-informed neural networks, okay? But anyway, here we will go over a very basic machine learning classification problem, okay? And the idea is that I'm gonna walk you through the code I prepared in a relaxed pace. We will also open and test, or not test, I mean check what the various libraries that we use do. Okay, so here is, for example, the joblib library that we will use to save our models and then load them into the web app. And yeah, I mean, this is the idea. And we will also use Gemini, okay? As you can see here, AI models are now built into the Google Colab environment. I actually never used them, so it's going to be kind of new to me. For example, here there is an add to Gemini. Okay, you can add files, I guess. You can add files from your local environment in Google Colab, okay. But anyway, let's test. So which LLM model are you, and what are you trained on? I think this is not going to work because we need to actually connect our notebook, okay, which is connecting actually because we opened this part here that lists the file found in our local environment. So okay, let's ask the AI and see what we get. Kind of slow. I think these are all built even in free versions of Google Colab. This is not the free version. I am a large language model trained by Google, so no more information. Okay, let's go to Google and say, okay, which LLM models are built into Google Colab? Okay, let's see. Access popular LLMs via Google Colab AI without an API key. I think this is Gemini. Okay, I mean, long story short, I think this is Gemini. Let's see. Yeah, it's Gemini. Sorry, the answer was simpler than I thought. All right, so we will be using Gemini whenever we want to do something extra from what I have here in the code, or when I don't know how to run a function that I want, or I will pretend that I don't know and stuff like that. So, okay, that's that. Also, this is a paid version of Google Colab. I'm not mentioning this because they are sponsoring me. I wish they did, but they don't. So let me show you. So Google Colab paid options. Okay, let's see. Okay, so this is the version I use, okay, the Colab Pro. costs 11 euros per month here in Europe, but I think it's the same in dollars in North America. So $11, I think it's the charge. You can also pay as you go, I think. I never used this. And then there is the Colab Pro Plus. Okay, it's too expensive. All right. So anyway, I use this because I enjoy working with machine learning problems, and I use this version to learn. So to learn and also be able to use advanced GPUs to run large models and stuff like that. So, but we won't use, we will not need any of this. This is a simple application, okay? Okay, let me walk you through. We will be doing basic machine learning classification with scikit-learn, PyTorch, and Dash web app, as I wrote over there. Okay, we will generate synthetic data using the make classification function. Make classification is, you can see it here. It's a function built into scikit-learn that builds synthetic data that you can use for classification and regression problems, as far as I am aware. But let's see what they say here. By the way, if you hover over a function that you import, it gives you information about that function. So let's see, let's go back. So, okay. So you can see make classification. You can specify the number of samples, the number of features. So these are your X features as they are used in machine learning, okay? Here I am assuming that you have some basic knowledge of machine learning, because I don't intend to teach anything. I'm just demonstrating what you can do, and then I will have a link to this notebook on GitHub, so you can use it and play around with it and learn for yourselves. You can specify the number of informative and the number of redundant features. And I think by redundant, they mean that, for example, a redundant feature will be a feature that is the multiple of another existing feature, okay? And you can specify the number of classes. This refers to classification problems, okay? So you can have a yes or no problem, or you can have a problem in which there are 3 classes or 4 classes or 5 classes and so on. Clusters per class, I never used that. I don't know what that is. You can specify weights to your features, I think. And anyway, so the description here says that it generates a random n-class classification problem. Oh, okay, sorry, I'm sorry. I think there is another function called make regression. So let me verify that, make regression. Yes. So if you want to create synthetic data for a regression problem, you can use this function. All right. So anyway, let's go back here. We will create 10,000 synthetic points with 4 features and 2 classes. Okay, so it's a yes or no problem, right? Then we will train and evaluate an XGBoost, classifier, a RandomForest classifier, a Logistic Regression classifier, a scikit-learn MLP classifier, okay? And I need to specify that XGBoost is not part of scikit-learn. You have to import it independently, and we do that, where do we do that? Here, okay? This is where we import XGBoost. And if you hover over that, it says XGBoost is the extreme gradient boosting library. No more information, but I will show you later what do we do with that. We also implement a simple neural network, which is similar to the MLP classifier. And the neural network is built with a very famous PyTorch library that is used for deep learning, okay? And once we build these 4 models, pretty much, is it 5? Sorry, 1, 2, 3, 4, 5. So XGBoost, RandomForest, Logistic Regression, MLP classifier, and then the PyTorch model, okay? So we will create these 5 models, compare them, and choose the 2 best in terms of accuracy, okay? And we will use those models to build an interactive web application using Dash. So the first step is to install and load various packages that we will need. So Jupyter Dash allows you to run the Dash library into a Jupyter notebook, okay? And what is the Dash library for those of you who don't know? So let's do Dash Plotly. So it's a framework pretty much that allows you to build web applications, okay? It doesn't have to be web applications that are relevant to loading and using machine learning models, but this is how I use it. This is how I use Dash here in this video, but you can do other things as well. I mean, you can build a web application to do anything you want using Dash. So their documentation is excellent. Because the first time I used Dash was before the era of LLMs, and I found it extremely straightforward to build web apps using Dash, okay? The underneath framework is Flask, I think, and Flask is another Python library, so Flask Python, okay? It's a Python library that allows you to build web apps as well, okay? And this is their web page. I will try to link to have links to all these things in the description of the video. And as you can see, there is a Flask in 1 hour full course by the Free Code Camp. I think it's that. Yes, I think it's that. So yeah, you can learn about Flask and Dash, etc. So anyway, we'll come back to that. All right, so here in this cell, we just install Jupyter Dash. And by the way, in Google Colab, most libraries that you will ever need are actually preloaded. So just try a simple import. And if it throws an error, it means that the library doesn't exist. And then just pip install them, okay? And you need the exclamation point in Google Colab environment or a Jupyter environment in general to install libraries. Okay, so the various libraries we need is NumPy for arrays and operations, pandas to create data frames, random for random numbers. Joblib is a very important library because it allows you to save the models you create, okay? These are various utilities from the sklearn library. So from datasets, as I already said, we will be using make classification to create a synthetic data set. We will use the train test split to create a test set and a train set. So the training set is used to train the models and the test set to test the models once they are built, okay? We will also be using the StandardScaler and various metrics that evaluate these models, okay, such as the accuracy score, precision and recall score, F1 score, the area under the curve for receiver operating characteristic score, and we will also be using the classification report, which is a nice table that summarizes all the classification metrics pretty much, okay? We will be using the RandomForest classifier, which is under the sklearn ensemble module, okay? And we can actually go online and find, okay, find all the ensemble based methods for classification. So as you can see, there are many of them. So RandomForest is one of them. There is also the voting regressor, the XGBoost classifier, and many other classifiers that you can use. So sklearn is a very mature module. It contains dozens of classifiers and regressors that you can play around with, okay, for your problems. So let's go back. From linear models, we will be using the logistic regression. And by the way, when we say a linear model, we mean a model that has parameters that are fitted during the training. Okay, so logistic regression is one of them, and let me show you why it's a parametric model. And ensemble models are not parametric models, okay, because these are, for example, RandomForest is a tree-based classifier, which means that it creates branches inside the data that you give it. So it decides, okay, if this quantity is larger than this number, I will say that this is a yes. If it's lower than this value, I will say that it's a no, and so on. Whereas logistic regression is an actual model. Let me show you. Here is the description of the model. Actually, what I want to show you is, maybe let's go to Wikipedia. And okay, this is what I mean. Okay. Actually, this is what I want to show you. So what I'm trying to say is that logistic regression models, and the same goes for linear regression, has parameters that are fitted during training. Okay, so for example, in this P of X probability density function that they show, the training parameters are Vita naught and Vita 1. Okay, so let's go back. As I said, we will also be using the MLP classifier. So it's this is a multi-layer perceptron classifier, which optimizes the log loss function using LBFGS or stochastic gradient descent. Okay, so you can specify which loss function you want, I guess. So this is also a non-parametric model. Okay, meaning that you fit. Actually, no, it is a parametric. I mean, neural networks are parametric models in that you have to fix the weights and the activations and so on. So what else? This is where we import PyTorch and the various tools needed to build a neural network. And this is the part where we import components for our web application. And we also specify the random state 242 and a random seed. And these are used for reproducibility. I mean, every time you run a notebook with the same random state and the same random seeds here, you will get the same result pretty much. Okay, so let's run this. Okay, it's gonna take a second, maybe a few seconds, because we need to install Jupyter Dash. I didn't get any feedback yet. Actually, I did get a lot of, I did get some feedback on my other videos where I talk about agent-based modeling and pins and so on. But it would be cool if someone commented below if this is useful or not. So anyway, okay, this is the setup cell, I guess. Okay, so this is where we import the libraries and so on. So let's move on. So in the second cell, we actually generate our data using make classification. Okay, we already discussed this. So this is how this function works. So make classification, and we can use it directly because we already imported it over here. Okay, so x and y is set using this make classification function, where we specify that we need 10,000 samples, 4 features, and all of them are informative, meaning that they are not linearly dependent. Okay, and we also need 2 classes, and we also use a random state. Okay, so here in this part, we actually turn x and y into data frames, and we specify that the name of the y, our label vector, will be target. Okay, and we also name the columns as F1, 2, 3, and 4 pretty much, okay? So these are our features in the data frame, and in the same data frame, target is our target, okay? And we then use train test split, and we set that to our test set to be 20% of the data. We use a random state for reproducibility, and stratify is an important variable to set. So this means that we maintain the percentage of true or false, or actually in this case, yes or no. We maintain the yes or no's that are found in the 10,000 samples into both the training set and the test set. So for example, if 60% of data are yeses in the full data set, then in the training data set and the test data set, we try to maintain that 60% of yeses, okay? I hope this makes sense. We also define a standard scaler, okay? And the standard scaler will be needed when we actually build the web app, okay? So we save it using joblib. And okay, let me run this cell and I'm gonna comment a little bit more. So actually, let's actually see the data frame. Okay, so as I said, this is the target, yes or no, okay? And these are our features, F1, F2, F3, and F4. If you want more information about the data, you can use this dot describe. It's a method of pandas data frames, and it gives you the statistics pretty much of the data frame. Okay, so we have 10,000 points. Actually, let's see. Let's test the Gemini. So, hi Gemini. If I want the stats of pandas data frame, which command can I use? Let's see. Let's see if the answer is the same as the one we used. Okay. It takes some time. I don't know why. So you can use .describe. Wow, okay. You have already used this in cell. Okay, this is some cryptic description of this cell, I guess. So it knows it. Okay, so it's all integrated into your notebook. That's cool. It provides information like count, mean, standard deviation, minimum, maximum, and quartiles for numerical columns. Wow, okay. So the AI works. Okay, that's great. So anyway, let's go back to this. Okay, so the mean value of the F1, for example, feature is minus 0.5. The standard deviation is 1.36. The minimum value is that. 25% of the data are below, minus 1.44. 50% of the data are below minus 0.67, which is also the mean, close to the mean actually, sorry. And the maximum value is 5.72. Okay, and then for the target, the mean is 0.5, which means that we have as many yeses as no's. So it's approximately 50-50. And I think to actually count, so the target is a categorical variable. Categorical means 0, 1, 2, 3, 4, 5, whatever. So here we have a target that takes on the values 0 and 1. So if we do df and then target, we target this column, okay, the last column only, okay? Okay, so it tells you that you have 10,000 rows, blah, blah, blah. But if we use this method called value counts, I think, yes, okay. It tells you how many positives and how many negatives you have. So you see that it's approximately 50-50, as I already said. So, okay, let's use describe. Okay, oops, describe the whole data frame. Okay. All right, so let's do one more thing, actually two more things before we move on. So what if we say that we have 3 informative and 1 redundant feature? Okay, what do you think the scribe will look like? So let's see. So okay, I don't see anything that stands out, so let's ask the AI. So how can I find redundant, okay, features in my DF? Okay, I'm referring to ideas such as correlation. Correlation matrices, and so on. Okay, let's see what it will say. Wow, it actually outputted a whole new cell. You can use a correlation matrix to identify redundant features. Highly correlated features might be redundant. Here is how you can compute and visualize the correlation matrix for your data frame. Okay, so it gives me the option of accept and run. I never used this before. Okay, that's crazy. Accept and cancel. Okay, let's do accept and run. So it created a new cell. Okay, and it does things here. I have computed and visualized the correlation matrix and also identified features with high correlation based on a threshold. It seems there are no highly correlated features to drop in this dataset. The next step in the notebook is to train the classical models. Okay, cool. All right, so because still not clear to me. Okay, first of all, we will go back to 4 and 0 for this. Okay, this is the describe function. And wait, where did the cell go? What? It removed it? But I wanted it. Okay. Oh, it's here. Okay. Evaluation of utilities. Okay. So I'm gonna move this cell there. Okay. It makes more sense that the cell is there. Okay. So when you run the correlation, you usually exclude the target. So, but anyway, this is how you can calculate the correlation between the features, okay? Highly correlated features are close to 0.8. So, for example, the correlation between F1 and F2 is just 0.13 in this case. So, let's go to Google. What do redundant features mean in make classification? Okay, these features are generated as random linear combinations of the informative features. Okay, so I was right that that if you use redundant features, these features will be linearly dependent on the informative ones. Okay, so actually AI made a mistake. I think the correlation you need to calculate in case, okay, let's go back to demonstrating that. I hope I'm not losing you. I hope this makes sense. So, okay, I have one redundant feature. Nothing stands out here to be able to tell which of the 4 features is the redundant one. So let's calculate the correlation of actually, okay, let me show you. So we need column F1, F2, F3, and F4. Okay, I think this is gonna work. Yes, it did. All right, we still don't see any redundant features actually. So features to potentially drop due to high correlation threshold of larger than 0.8. Okay, none is really redundant, but anyway, I guess you can use make classification to introduce redundant features anyway. So let's move on actually. Okay. Oh, I haven't talked about the StandardScaler. Let's hover over that. Okay. So what does the StandardScaler do? Standardize features by removing the mean and scaling to unit variance. The standard score of a sample X is calculated as, okay, centering and scaling happen. Okay, actually, let's ask the AI. So what does the StandardScaler do? So what it does pretty much is to scale everything between 0 and 1. But let's hear it from the AI. So let's see what it says. By the way, I checked, and all the things I'm using here are available in the free version of Google Colab. It's just that it's slower, okay? So the StandardScaler is a pre-processing technique in scikit-learn. It standardizes features by removing the mean and scaling to unit variance. This process makes the mean of each feature 0 and the standard deviation 1. It's often used to improve the performance of machine learning models that are sensitive to the scale of the input features, such as those that use distance calculations. Okay, so actually let's go see what the result of this is. So, okay, let's go over here. So x-trained scaled. You see that this is an array that runs from, actually let me show you something else you can do. So pd dot DataFrame. Okay, I think this will work. Okay, module pandas has no attribute. Okay, maybe this. Yes. Okay. Okay, so you create a data frame by inputting an NumPy array such as xtrain scaled, and then you can do describe as we did before, and this will give you the mean, which is 0. Okay, I mean 10 to the minus 18 is 0. Okay, standard deviation is 1. The minimum is that, and the maximum is that. Okay. Something bothers me. Let me see. Actually, can we plot this? I want to see. How can we plot the distribution of xtrain scaled of one of the features inside xtrain scaled? Okay, let's see. Okay, like before, it actually throws out, it throws the code. Okay, let's check. Xtrain scaled, it creates a data frame like I tried to do here. Okay. And then it uses a hist plot. Okay, I forgot about that. It's a histogram plot, and you can find that in the Seaborn library. Okay, so let's run this. What I was hoping for, maybe I made a mistake here, but this will work probably. I think what I had in mind is the min max. Okay, let me try something. Min max scale. Okay. Is not defined. Okay, we have to import it. Let's go back here. Actually, Okay, we need this. Okay, mean. Okay, this should work. Yes, okay. And now this scales everything to, let's see, let's go back to this plot. Okay, so the min max scaler scales everything between 0 and 1, as you can see. Okay, so all the values become, get transformed between 0 and 1. Okay, but okay, let's keep the standard scaler that we had in the beginning. So the standard scaler pretty much forces your data to, let's go back to the plot. It forces them to have a mean of 0 and a standard deviation of 1. Okay, that's all it does. Okay, now what else do we have in this cell that needs to be addressed? Once you define the scaler, you have to transform your xtrain using fit transform and your xtest using transform. Okay. Okay, I feel I owe you a better explanation of what of how scalars work. So once you define them, you have to train them. Okay, so fit transform fits the data, then transform it. Okay, so in this step we use just the training set. Okay, to fit the scalar. So we fit the parameters of the scalar, and then once the scalar is fit, we just use it by using the transform function. We just use the already trained scalar to transform the test data. Okay, that's all. And we also save the scalar so we can use it later in the deployment phase. All right, so let's move on to the next thing we need to do. Actually, let's also save our notebook. So, okay, in this cell, we create a helper function that allows us to actually calculate the accuracy, precision, and recall and F1 scores for a particular model using the true labels and the predicted labels. Okay, and this Y proba is a two-dimensional vector that some models output that gives you the probability that you have a yes and the probability that you have a no. So this is for example an array in which each row, the sum of the numbers in each row sum to 1, because it's a probability that you get a yes in the first column, and the second column is the probability that you get a no. Okay, and if you do give this helper function this Y proba array, it calculates the ROC score. Okay, and yeah, there is not much to this function, so I'm just gonna walk through this and move to the interesting part, which is to train what I call the classical models. I don't know if there is such thing as classical machine learning, but I mean, these are the standard shallow models, as they are called. The standard shallow models that are used in various machine learning problems. And shallow refers to the fact that this is not, these models are not deep, like a deep neural network that has various layers. It's just one layer, pretty much. Okay. All right. So LR is the logistic regression. We use a random state to initialize. And you just call the fit function, and you see that's exactly the same thing in all of these models. Okay, so this is a nice thing with machine learning libraries. Once you learn how to use one model, you can probably use any other model just by typing things in. And now with the AI models, you will get suggestions, and you can also go back. You can always go back to the documentation of a model that you are using and find everything you need to know about it. So for example, if we go to the RandomForest classifier, here we get the description of the class itself, because the RandomForest classifier is a class, okay, that has various parameters that are listed here. and methods that are used that are listed probably at the end. Let me see. Okay. Okay, examples. Okay, yeah, these are the methods. They are not called methods for some reason, but these are the methods that you can use. So apply, decision path, fit, etc. And then they also give you the parameters that you need to pass in each of these methods. So what you do here is to fit our data to the various models. Okay, so we have the logistic regression, the random forest. We can specify the number of estimators, and these are the so-called hyperparameters of models because you can change them and see what happens if you change them. Okay, and there are many more parameters that you can play around with. So here I listed only the most basic ones. Okay, so you define the model, you fit the model, you calculate the prediction by using the test set. Okay, so you need to use the X test scaled, and the logistic regression allows you to calculate the Y test proba, the thing we talked about here, which gives you a two-dimensional vector. A vector with two columns. Okay, the first column is the probability for a no, and the second column is the probability for a yes. Okay, so you can do that with logistic regression, and then you pass everything into this function we created here, which calculates for you all the metrics that are defined over here. Okay, and it also prints a classification report. So okay, the Y test proba is something that can be calculated for all these models pretty much. Okay, and then we just save these models using joblib dump. So it's the same as we did with the StandardScaler before. Okay, so let's run this. It's going to take a second. These models are run fast. So for example, the logistic regression, okay, here are all the important metrics. So you see, okay, the classification report is kind of cool because it gives you the precision and the recall together for the 0 class and the 1 class. Okay, and support means how many data points were used. Okay, so I mean, if you just use the accuracy, this is not a good model. Okay, logistic regression is not usually good to use in machine learning, but it's a nice toy model you can use to when you play around with your data. Okay, RandomForest is much better. You can see that, and it actually outperforms XGBoost. The precision in the 0th class is good, and the same goes for the first class. And by the way, here we actually use the 2000 test points, okay, to calculate these metrics. This is why it's 2000, because remember we have 10,000 data points, and we split our data set into 80% training and 20% test. So 20% of 10,000 is 2000. Okay, and this is the XGBoost results. Okay, and that's it. I mean, training's done. That's it. I mean, it's simple as that. Okay, it's simple for the first step. I mean, if you want to optimize these models, you have to do you have to use some base classification and this kind of things. So grid search CV, for example, is a nice algorithm that can be used to optimize your hyperparameters. So I'm not going to demonstrate this today because it's a mess. It takes some time. So we will move on. The next step is to use the multi-layer perceptron classifier, which is very simple to use, pretty much. I mean, you use exactly the same methodology as you use for these models, okay? And what you have to specify in this classifier, because this is a neural network, is the number of layers, okay? So these are your layers, okay? 128 means 128 nodes. And then in the second layer, you have 64 nodes. And in the third layer, you have 32, okay? This is the number of iterations. This is the solver used, which is called the Adam optimizer, okay? It's what allows for the gradient descent process to go on. And for activation, we use ReLU, and ReLU looks like this. So activation, let me show you a function. So rectified linear unit. So this is what it looks like, the blue line, okay? So it's 0, and then it becomes a linear function for values of x larger than 0, okay? All right. I want to talk more about this. You just fit it and then evaluate it, and you do the same steps as we did with the other model. So there is nothing different really. I just had it in a different cell because this is a neural network, okay? And it takes a little bit more time to train. So let's see what the result will be. So the accuracy is quite good actually, okay? And we will talk about that later. But now let's use PyTorch to do exactly the same, okay? So with PyTorch, you need to define a class for your neural network that inherits from this neural network module, okay? So if you use this, if you build your class like that and you inherit from the neural network module, you have to use this super.init, which means which initializes this module, okay? And then you define various things that you want. So for example, the input dimension is 4. This refers to our 4 input features, okay? So our first layer will have an input of 4 units for our 4 inputs and an output of 128 layers. And then the second layer will have an input of 128 and an output of 64. So we are mimicking this classifier pretty much, okay? So you need to have a matching between the output of the first layer and the input of the second layer, okay? So the output of the second layer has to be the same as the input of the third layer, and the output of the third layer has to be the same as the final output, okay? So we have 3 hidden, we have 3 hidden layers pretty much just like here. And we have the input layer, and the output is just 1 because we have binary classification, so yes or no. Okay, and with neural networks, you have to define the forward function, and x is the sample, like so 1 row from, okay, let me show you. So remember this data frame. So this x refers to this, or this, or this, and so on, okay? So in each forward pass, when the optimizer runs the model, you feed it into this network, okay? So we define the batch size to be 128. So we are training in batches of 128 pretty much. We need to use, we need to define a training and a test data set, and these have to be converted into tensors. So we use the tensor dataset from Torch, and we imported this up here, if you remember, over here. So, okay. So let me see. we turn our data into PyTorch tensors. Okay, this is what we do here, and then we load the data. So we need this training data set pretty much so we load it into a data loader for PyTorch purposes. So we do shuffle our input, but not our output. We specify the device that will be used for the training. Then we just define the model and the input dimension for the model, and we send that to device. The criterion for the optimization will be this BC with logic loss. So let's find the definition. So BC with logits is, let's see. This loss combines a sigmoid layer and the BCE loss in one single class. This version is more numerically stable than using a plain sigmoid. Okay. Okay, and then we need to define an optimizer, which is the Adam optimizer, just like here. Okay. This is standard PyTorch workflow when you train neural networks. So we pass the model parameters as the thing to be optimized and the learning rate, okay, for the gradient descent. And then we define 30 epochs. In this case, actually, let's do 100. Okay. Best test load. Okay. Best test loss. Okay. So this is the loop pretty much. Okay. So in each loop, we have to call model.train, set the total loss to 0, and then we will take the data from the train loader, send them to device, call the optimizer and do a 0 grad, and then calculate the logits, calculate the loss, and YB are the true labels here, and logits are the calculated probabilities, okay? And then we do loss backward, and then we take one step in the optimizer, calculate the total loss, and the average training loss is calculated once all the data have been used pretty much, okay? So okay, once that's done, we evaluate the model, and with torch no grad, we calculate, let me see, the final probability pretty much, okay? So this is in my GitHub. I'm gonna just run it here, and we actually save the model somewhere. Where is it? Let me see. So, okay, let's run the model. So you see how the training loss and the test loss drops. Okay. With each epoch, and things kind of stabilize over here, but we keep the training. So this goes fast because these are tabular data. Okay, and these are our final results. So in this cell, we just compare the models we calculated. So the logistic regression, the RandomForest, the XGBoost, the MLP, and the torch. And we selected best two, which is the PyTorch and the RandomForest. Here we just verify that all of our models are saved, which they are. And finally, my favorite part, which is the Dash web application with a vintage modern theme. So, all right. So we have to load the scaler in the web app because we will need that. Here we actually load all the models, but we pick the best two. Okay. What else? If path exists, okay, let me move on. So threading is, let me talk a little bit about that. So this is used to emulate a subset of Java's threading model. I'm sorry. So these are used to be able to show a web application here in Google Colab. Okay. We use the Montserrat CSS pretty much. So actually, if you press Command on your keyboard or Control, if you use Windows, this becomes clickable, so you can click it. And here we have various definitions of fonts and styles relevant to this Montserrat font. Okay, that is used for the web app. These are various colors used for the text, the accent, the card, and the background. So if you actually Google this, it will show you the color, I think. So yeah, so this is the color we will be using for the background, for example. This is just white for the cards. This is hexadecimal, so okay. So you see that this is white. This is brown. Okay, that color, and so on. Now, the first step is to define the layout of your web application. So this is what you do here. Okay. So let me see. Now I'm a little bit confused. Okay, the div stops there. And yes, okay. So you see that you define an HTML div, which for those of you who are into web development, this is just a div. This link specifies that we will be using this style sheet. Okay. The second div specifies an h2 header that tells you that this is the machine learning classifier demo, and you can define styles into these h2 elements. So actually, let me show you. So if we go here, html.h2 dash. Okay. As I said, the documentation of Dash is excellent, guys. Okay, and again, I'm not being sponsored by them. I wish I did. So I guess this is a shout out for sponsoring, but their documentation is great. So this is an H2 component, so header of level 2 pretty much. Okay, so in all of these elements, you can tweak various parameters, as you can see over here. Okay, and you can specify a style over here, and styles are defined as dictionaries. So style defines CSS styles, which will override styles previously set. Okay, so in this case, the previously set style for margin bottom will be overwritten to 5 pixels, for example. Okay, and in the same layout, which is a div, we add another div that has some text that displays this text pretty much. Enter 4 features, choose a model, and get a prediction. Then the next div over here, which is a large one, defines the labels, defines a drop-down menu, which this with this ID, and let me see. Okay, and then wait, is this in the same div? I forgot now. Okay. All right, you can see the code later. The most important part of the code is this callback over here. So the output means that this callback will modify the prediction output and the probability output, okay? So it will modify the content of these two divs pretty much, okay? And to modify the trigger function will be the predict button. So this is the button that we will be pressing to get a prediction pretty much, okay? So this will trigger the callback of this function, okay? And state means that these are parameters needed for this callback to work, okay? So this callback, once it's triggered by pressing the button, it goes here into this function that takes into as input the number of clicks, the model name, and the four parameters F1, F2, F3, and F4, which recall that these are our features, okay? So the user can enter these features, the model name, and click, and once it's clicked, okay, if not clicked, nothing's happening, but upon clicking, we create an array that takes this input, it transforms it. Remember that we need the scaler to transform the data because the models were built using the scale data, okay? So we need to transform our data before passing them to the model. So if the model name is one of these, load the model, get the probability using the X-scaled, get the prediction. Okay, if the model is PyTorch, we have to do things a little bit different, as you can see here. And the label is yes if the prediction is 1, else no, and return the predicted class. So this is going to be returned pretty much to this div over here, the prediction output. I'm sorry. So this part, okay? And run here just runs the app. These are standard parameters. The host is 0.0.0.0. The port is that. Debug is false. And then this thread allows you to actually run. So here we just call this run function. So this allows you to run the app in Google Colab. And let's run it. Okay. You see it's loading. And this is our web app, okay? So, for example, you have the RandomForest and the PyTorch net. So in feature 1, actually, let me remember. So let's do df. Okay. Actually, let's do dot describe. I'm sorry. Dot description, I think. Okay, no. What am I trying to do? No, I got confused. I'm sorry. df.describe. This is what I need. Okay. I don't know why it didn't work. Did I have a typo? Maybe I did. So, but anyway, so the actual data that we have, okay, so for example, F1 goes from about -5 to 5.7. So let's enter 2.8. Then F2 goes, okay, has a mean value of 0.01. So let's do 1.3. For feature 3, let's do 1.5. I'm just checking that the values that I give here are within the model, okay, within the distribution of the variable pretty much. So So F3 goes from -6 to 4.8, so 1.4 is a good value, and F4 goes from -5 to 5, so let's do -3. -3. Okay, and let's do predict. So the predicted class is a yes with 99.5, so almost 100% probability with RandomForest. Let's do PyTorch and see. So it also predicts yes with a 99.9% probability. Okay, so this is these are some basic things you can do with machine learning and web apps. So things are kind of straightforward until they are not, but you can easily train models nowadays using these really nice libraries. So I haven't done anything really. I just called functions that are already made, okay? And I also built a web application for these models, okay? And the inspiration for this video, I guess, was actual research work that I did. Let me show you. Okay, this is my academic profile, I guess. So over here I say, okay, this was built with a different framework, and okay, it's a little bit more involved to show this in a video, but this is Streamlit. It's another framework used to build web applications with Python and deploy machine learning models that way, okay? And here I have drop-down menus where the user can enter values and get a prediction for the sex of a skeleton, okay? So this is what this application does, for example. So as I said, as I promised, I'm gonna try to have a GitHub and upload this code for you guys. Let me know in the comments if these videos are useful. I'm just still experimenting with what can be done on YouTube in terms of teaching. And I'm gonna be back with more videos like this. So yeah, I'm gonna stop the video here.